Hello, Becky. I'm going to go through the 2021 stats paper. Yeah, let's just get right into it. Okay, so question one says New Zealand is well known for their cafe culture, and the availability of coffee has increased significantly over the last 20 years. However, there's growing concerns that teenagers are consuming more caffeine with potential negative effects on sleep behaviors and performance at school. A school was concerned about this issue and conducted an online anonymous survey of 300 of its senior students. It asked if students drink coffee regularly, at least 3 times a week, and if they have any sleep-related issues. And this result is summarized in the table below. Okay, so we see our two categories: if they drink coffee regularly or not, and if they have sleep issues or not, and then a total of 300. So, according to this survey, what proportion of senior students drink coffee regularly? So drink coffee regularly is going to be this one over here, and it doesn't ask about sleep issues, so it's all of them that drink coffee regularly, so it's 122, and it's about all the senior students, so it's 122 out of the 300. So our answer is simply going to be 122 out of the 300, which you can convert to a decimal of 0.4067. Okay, next is, what is the probability that a randomly selected student from the survey who has sleep issues also drinks coffee regularly? So this is a condition where it's a selected student from the survey who already has sleep issues. So those who already have sleep issues, we're looking at this column over here. So our new total is going to be the 143, and we're looking at for whether they drink coffee regularly, which is the 68 of them that drink coffee regularly. So that's the 68 out of the 143. And that gives us a probability of 0.4755. Okay, next is, Jack looked at the data for students with sleep issues and noticed that fewer of them drink coffee regularly. He claims that this means that it is less likely for coffee drinkers to have sleep issues than those who don't drink coffee. Explain Jack's reasoning and justify why he's wrong with appropriate calculations. So what Jack is looking at the total number of those who have sleep issues and then comparing them straight off the bat. So saying that, well, there's 68 of students who have sleep issues that drink coffee regularly compared to 75. So therefore, there's more people who actually have sleep issues who don't drink coffee regularly. And so he's making that claim. So he's looking at the total numbers, but he's not considering the proportions. Because if you look at the proportions over here, right, of the students who drink coffee and those who don't drink coffee, the proportions of them are different, right? Those who do drink coffee regularly, there's only 122 of them, and those who don't drink coffee regularly, there's 128 of them. So there's different proportions here, so there's going to be different probabilities when you add that condition in. So we're going to compare the conditional probability of those who have sleep issues given that they drink coffee regularly, and compare that to those who have sleep issues who don't drink coffee regularly, given that they don't drink coffee regularly. So we can actually check the proportions of each of the categories and compare them, and not just an outright number, because this number doesn't take into consideration the differences in the total number of students that are being interviewed in that category. So here, the probability of those who have sleep issues, given that they are a coffee drinker, is equal to the 68 of them out of the 122 in total, right? So it's these two. And that will give us a probability of 0.5574. And then compare that to the probability of if they have sleep issues, given that they don't drink coffee. So you can say no coffee. And that was the 75 students that drank coffee, given that they don't drink, 75 students that had sleep issues, given that they don't drink coffee, so it's 178 of them. So that will give us a probability of 0.4213. So now, taking into account the proportions, you can see that those who do drink coffee, there's a higher proportion of them that have sleep issues of 0.5574 compared to those who don't drink coffee that have sleep issues of a probability of 0.4213. And so you can take a relative risk here. So the relative risk here, and you can kind of bear in mind the direction of this claim here. He claims that this means that it's less likely for coffee drinkers to have sleep issues compared to those who don't drink coffee. So the comparison group is going to be those who don't drink coffee and the affected group is going to be the coffee drinkers. So this is going to be the coffee drinkers divided by the non-coffee drinkers as our comparison group. So this is the 0.5574 divided by 0.4213, which gives us a relative risk of 1.323. So this actually tells us that those who have sleep issues, given that they drink coffee, have a 1.323 times likelihood to have sleep issues compared to those who don't drink coffee. So we also need to take into account explain Jack's reasoning. So Jack was only looking at total numbers, not taking into account the proportions. The proportions out of the total in each category. So he is wrong here. So yeah, these calculations justify that he is wrong. Okay, next. So this is the same table. And part B is, it is well known that many of the popular energy drinks consumed by teenagers in New Zealand contain caffeine in even higher doses than coffee. The same survey also asked about the consumption of energy drinks. It found that 36 students didn't drink coffee but did drink energy drinks, and then only 7 of these students who drank energy drinks but not coffee had no sleep issues. So they want us to fill out this table below. So we've got new categories here. So the first bullet point that says 36 students didn't drink coffee but did drink energy drinks, so that is this row over here, and there's 36 of them, so our total is going to be 36 over here. And then of these students, so it's still looking at this row, 7 of them had no sleep issues, so 7 of them had no sleep issues over there. So we just need to fill out this table. So all of this must add up to, so these two must add up to 36, so the missing value must be 29. And then these 3 must add up to 143. So 143 minus 29 minus 68 gives us 46. And then over here, 157 minus 7 minus 54 is going to be 96. And then these two added together should give us the total over here, which is going to be 46 plus 96, 142. Okay. If there were 850 senior students in the school who don't drink coffee, who don't drink either coffee or energy drinks, how many of them would you expect them to have sleep issues? So we again have a problem with conditional probability combined with expected number. So you have 850 senior students in total, but you want to find the probability that they have sleep issues given that they don't drink either coffee or energy drinks, because the condition here is, when you read it, who don't drink either coffee or energy drinks. So we're only looking at those who don't drink coffee or energy drinks. So the probability of them having sleep issues, given that they don't drink coffee or energy drinks, is equal to, so we're looking at those who don't drink coffee or energy drinks, and then if they have sleep issues, which is the 46 of them. So it's the 46 out of the 142. And that gives us a probability of 0.3239. And the expected number is going to be the number of students multiplied by the probability. And we have here 850 students multiplied by the probability of 0.3239, which gives us 275.35. Now, bear in mind, you can't have 0.35 of a student, right? You can only have whole numbers of students, so you get it either round up or round down. In this case, I'd round down to 275 students will have sleep issues, given that they don't drink coffee or energy drinks. Okay, next is a newspaper article claimed that teenagers in New Zealand who consume drinks containing caffeine regularly are nearly twice as likely to have sleep-related issues as those who don't consume drinks containing caffeine. Discuss whether the school surveys provide sufficient evidence to support the validity of this claim. So there are two main parts of this. One is the calculation part to validate the claim using a relative risk, but then there's also a second part that wants you to evaluate the transfer of findings. So here the claim is that teenagers in New Zealand, right? But this survey is taken in one single school. So you have to consider whether or not one single school's worth of data is representative of all the students in New Zealand. Probably not. So that's a point that we're going to add inside there at the very end. The first part about calculating it, though, is calculating the relative risk between those who consume drinks containing caffeine, so those who consume containing caffeine regularly, nearly twice as likely to have sleep-related issues as those who don't consume drinks containing caffeine. So it is important to note here that you have to combine these two categories as those who do drink caffeine or caffeinated drinks, and then this one over here is the one that has no caffeine. Right, because coffee and energy drinks contain caffeine, so you have to combine them together. And we're looking at those who have sleep issues, right? And so we have to consider the conditional probability here of having sleep issues given that they drink caffeine or given that they don't drink caffeine. So those who have sleep issues, given that they drink caffeine, is going to be looking at these two rows because that is the condition of them drinking caffeine, and then those who have sleep issues. So the conditional probability here is going to be the summation of both the groups. So it's going to be the 122 plus 136. So that's the total group. And then those who have sleeping issues are the 68 plus the 29. So the probability of having sleep issues, given that they consume caffeinated drinks regularly, is going to be the 68 plus the 29 who suffer the sleep issues over the total number of those who drink the caffeinated drinks, which is the 122 that drink coffee, and then the 36 that drink the energy drinks, which is 97 over 158. So this probability gives us 0.6139. And then the next part is that the probability of them having sleep issues given that they don't drink caffeine. So it's looking at just this row over here. So that's the 142 total students that don't drink either coffee or energy drinks, and then the 46 of them that had sleep issues. So it's 46 over 142. So the probability of sleep issues given that they don't drink caffeine is the 46 over the 142, which gives us 0.3239. Okay, and then taking the relative risk here. So again, bear in mind the direction of the relative risk here. The relative risk is saying that teenagers who do consume caffeine regularly are twice as likely to have sleep-related issues compared to those who don't drink caffeine. So our control group is those who don't drink caffeinated drinks, so they're going to be our denominator. So it's going to be caffeine divided by no caffeine. So this is 0.6139 divided by 0.3239, and that gives us a value of 1.895. So this tells us they are 1.895 times more likely to have sleep-related issues if they drank caffeine compared to those who don't drink caffeine. So let's just put that in words. Based on this data, on this survey, it is 1.895 times more likely for students who consume caffeinated drinks to have sleep issues compared to students who don't. So you can say that because it's not over the threshold of 2 times, because the claim was that it is, the claim was nearly twice as likely. So you can say that because it is close to 2, that it is kind of valid, that it's nearly twice as likely. So 1.895 is close or reasonably close. To 2 times. So therefore the claim is partially true. Yeah, because it's nearly twice as likely. And then we need to address the second part of whether or not this claim is valid when applying to all teenagers in New Zealand. So you'd say here that the transfer of findings is not possible because it's just one survey of only 300 students of one school. So the actual sample size of 300 students, that's a pretty reasonable sample size, but because it's just one single school, it's biased and not representative of all the students in New Zealand. So, however, the sample was taken only from one school in New Zealand, therefore transferring the findings to all NZ students may not be representative. / may be biased. Another consideration you can have here that not just energy drinks or coffee contain caffeine. So also coffee and energy drinks are not the only sources of caffeine. You can give the example tea. So it may also not be representative. So you're looking at limitations of these studies and seeing whether or not you can actually transfer these findings and discussing the validity of them. Okay, question 2 is the use of plant-based milks in New Zealand has become much more popular in recent years. Cafes also now offer their customers a number of alternative milk options such as soy, almond, or coconut. Jung Woo owns a cafe and has collected data of his coffee sales over the last few weeks to find out how much he should stock alternative milk products. 40% of his coffee sales were to younger students. 1/4 of younger students requested an alternative milk type. 80% of older customers who ordered a coffee with cow's milk. Of the young students who ordered a coffee with alternative milk, 15% ordered soy milk, and then half of the older customers who ordered coffee with alternative milk ordered soy milk. So we are looking at a tree diagram here with multiple different categories here. So the first category being younger customers, so it's either younger or older, right? So our first category can be age. Secondly, it's going to be whether they requested an alternative milk or cow's milk. So it's going to be milk type. And then the third category is going to be, if it were an alternative milk, is it going to be soy milk? Because there are other options here, soy, almond, and coconut. So then we can put another category here of alternative type. So we can then draw our branches, age, young, and then old, and then milk, whether it is alternative, and then whether it is cow. The reason why I've drawn the branches at different lengths is because alternative will further go on to soy, and then the other alternative is not soy. But we aren't given the probabilities of those for almond and coconut, but it may be used for further questions. So let's fill out this tree diagram here. So 40% of his coffee sales was to younger students, younger customers. So that is the 0.4. And then so therefore older must be 0.6 because they add up to 1. And then 1/4 of younger students requested an alternative milk. So 1/4, 1 over 4 is 25% or 0.25. And so therefore those who ordered cow's milk must be 0.75 because they add up to 1. And then 80% of older customers who ordered a coffee with cow's milk. So then that is the 0.8 that ordered with cow's milk, and then 0.2 with alternative milk, therefore. And then of the younger students who ordered a coffee with alternative milk, 15% ordered soy milk. So that is 0.15 with soy milk, and so therefore 0.85 with a different type of alternative milk. And then half of the older customers who ordered a coffee with alternative milk ordered soy milk. So that is the 0.5. Okay. So this is our tree diagram. So the first question is find the probability that a customer in this cafe is younger and orders a coffee with cow's milk. So they are younger and they ordered coffee with cow's milk, right? So it's these two branches multiplied by each other. So this is going to be 0.4 times 0.75, which gives us 0.3. Cool. And then the next is going to be find the probability that the randomly chosen customer orders coffee with soy milk. So those who order soy milk are going to end with soy milk as their milk choice, which is going to be here, and it's going to be over here. So notice how it's two different branches that need to be added up together. So it's going to be young, and then alternative, and then soy milk. So that's one route, but then the other route is going to be old, and then alternative, and then soy milk. So you have to calculate the probabilities of each one of these pathways and then add them up together. So this is going to be, so the young route is going to be 0.4 times 0.25 times 0.15 plus the old route, which is 0.6 times 0.2 times 0.5. So adding up these together gives us 0.075. So that's the probability of customers choosing soy milk overall. So the next question is, out of the customers who request an alternative milk, what percentage of order a coffee with soy milk? So this is, out of all of them who request an alternative milk, what percentage of them actually order them with soy milk? So the percentage here is going to be, it's kind of a conditional probability. So the condition is that they order alternative milk, so they're given that they're ordering alternative milk, and then what proportion of them are actually ordering soy milk. So probability of ordering soy given that they're already ordering an alternative milk. So alternative milk is going to be the probabilities added up from this one and this one over here. So it's going to be this branch added with this branch that give us the probability of customers ordering alternative milk. And then of those, how many of them or what proportion of them actually ordered soy milk, which we actually just calculated in the previous question below. So actually what we're interested in here is probability of soy divided by probability of alternative milk. And the probability of soy we already know as 0.075. And the probability of alternative milk is going to be those two branches together. So 0.4 times 0.25 added with 0.6 times 0.2. So that is going to be, so down here, we've got 0.4 times 0.25 plus 0.6 times what was it? 0.2. So that will give us 0.075 divided by 0.22, which gives us 0.3409, and you have to convert this to a percentage because they asked for a percentage specifically. So you times that by 100, you get 34.09%, and that's it. Okay, the probability that a randomly selected customer ordered an almond milk is 0.066. So now we're considering almond and coconut milk. So of those who requested alternative milks, there were equal proportions of those ordering almond milk in each age range, younger and older, while the rest of the customers ordered a coffee with coconut milk. So how many times more likely is a customer to order coffee with a cow's milk than coconut milk? Okay, so let's just copy and paste this tree diagram over here onto here, and we can edit it. So instead of not soy, we want to break this up into two parts, whether it is almond milk or it is coconut milk. Okay, and we are told that there are equal proportions of those ordering almond milk in each age range. And we aren't actually given a probability for that, so we're going to let that equal x, right? That's going to be our unknown probability. And then once we solve that, we can then solve for the probability of the coconut. And this is useful because it says here in the first sentence that the probability of a randomly selected customer ordering an almond milk is 0.06. So this is of all customers, so it's going to be this branch plus this branch is equal to 0.066. So going through these branches, it's going to be the young who get an alternative and then get an almond. So that's the 0.4 times 0.25 times x added with the old, which is the 0.6 times 0.2 times x. And that both added together must equal to 0.066. So 0.4 times 0.25 times x plus 0.6 times 0.2 times x must equal 0.066. So this over here gives me 0.1x. This one over here gives me 0.12x. So this is 0.22x is equal to 0.066. So then x is equal to 0.066 divided by 0.22, which gives me a value of 0.3. So this probability over here is 0.3. So therefore, the final probability of coconut must be 1 minus 0.3 minus 0.15, which gives me 0.55. And the next one, this one again being 0.3, is going to be 1 minus 0.3 minus 0.5, which gives me 0.2. So now, the reason why we did this is because we want to find the probability of coconut milk and then compare that with cow's milk. Cow's milk we already have, but we want to find the probability of getting coconut milk. So now, probability of coconut is going to be this branch over here plus this branch over here. So it's going to go through young, alternative, and then coconut. Old, alternative, and then coconut. And added those two together to find the probability of coconut. So this is going to be 0.4 times 0.25 times 0.55 added with 0.6 times 0.2 times 0.2. All of this gives me 0.079. And then the probability of cow's milk is going to be this branch and this branch. So that's simply just going through young and then cow, old and then cow. So this is going to be 0.4 times 0.75 plus 0.6 times 0.8, which gives me a probability of 0.78. So then calculating the relative risk, because it's asking for how many times more likely is a customer to order coffee with cow's milk. So this is, the direction is comparing cow's milk compared to coconut milk. So the comparison group is, or the control group is going to be coconut milk. So that's going to be in the denominator. So the relative risk is equal to the cow's milk divided by the coconut milk probabilities, which is the 0.78 divided by 0.079, which gives me 9.873. So they are 9.873 times more likely. And that's my answer. Okay, next one. Kathy prefers to drink a flat white coffee with milk, but is allergic to cow's milk and dislikes soy milk. When she goes to a cafe for the first time, if it does not have an alternative milk available, she will order a long black coffee. She finds that this happens 30% of the time, okay? And that's what we see over here. 30% of the time she gets a long black. She has found that out of the cafes that offer alternative milks, about 40% have both almond milk, so 40% have both almond milk and coconut milk available. If the cafe has both almond and coconut milk available, she flips a coin and chooses either one randomly. Kathy has also noticed that if a cafe has only one non-soy alternative available, it is twice as likely to be almond milk as coconut milk. So we need to fill in this tree diagram to then work through it. So the first one, long black or flat white, these add up to 1, so this is 0.7. And then again, these must add up to 1 as well, so this must be 0.6. And then if both of them are available, she is said to flip a coin, right? And flipping a coin gives you equal chance of getting both, so 0.5 and 0.5. And then if only one is available, then it is twice as likely to be almond as coconut. So you have twice as likely compared to 1, which means that there are 3 lots of options here, 2 and then 1/3. Sorry, this should be a plus. So this must be 2 plus 1/3, which meaning that the probability of getting almond is 2/3. And the probability of getting coconut milk is 1/3 because they are almond milk is twice as likely as coconut. So there's a 2-to-1 ratio. 2-to-1 ratio gives you 3 total options, and then almond has 2 times more, so it occupies 2, and then coconut occupies 1 of those chances. So yeah, that's the explanation of the 2/3. So it's not 1/2 and then 1/2 because that's equally as possible. Anyways, overall, it is it more likely for Kathy to have a long black, an almond milk flat white, or a coconut milk flat white? So we just need to go through each one of them. So her having a long black is just this option over here, right? And then her having a almond milk flat white is going to be this option plus this option. And then the probability of her getting a coconut milk is going to be this option. Oops, sorry, wrong color. Is going to be this option plus this option. So probability of long black is simply 0.3. Probability of almond is going to be going through flat white, both available, and then almond, or the flat white, one available, and then almond. So adding those up is going to be 0.7 times 0.4 times 0.5 plus 0.7 times 0.6 times 2/3, which gives me a probability of 0.42. And then the probability of coconut is going to be going through flat white, both available, coconut, flat white, one available, coconut. So multiplying those probabilities together, 0.7 times 0.4 times 0.5 plus 0.7 times 0.6 times 1/3. And that gives me 0.28. So obviously the one with the highest probability is the one that she is more likely to get, which is going to be almond milk. So she's more likely to get that. And that's it. Okay, question 3. A cafe manager notices that the amount of time a customer waits to receive their takeaway coffee varies. He collects some data over a week and finds that the mean is 7 minutes and an estimated standard deviation of 1.5 minutes. Assume that as a normal distribution, blah, 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 and working and or diagrams must be shown. So find the probability that a customer receives their coffee within 5 minutes. So this is within 5 minutes. This is the probability that X is less than 5 minutes. So graphing that, if you have a distribution, right? Normal distribution centered at the mean of 7 minutes and a standard deviation of 1.5. So where it's less than 5 is going to be to the left of the center, where it is 5, and then the probability of less than, which is the area to the left of 5. So putting this into your calculator with a standard normal distribution with a mean of 7, standard deviation of 1.5, in CD for cumulative, and then your upper boundary being 5, lower boundary being a really negative number, so like a negative 1,000, and you should get 0.0912. Okay, next is one day the cafe has 150 customers who order takeaway coffee over the afternoon period. How many of these coffees would you expect to wait between 8 and 10 minutes for their coffee? So this is when X is between 8 and 10. So again, graphing this, centered at 7, and so between 8 and 10 is going to be here to here. So the area between 8 and 10, what is the probability of that? So same things, but with your lower as 8 and your upper as 10. So that is going to give you a probability of 0.2297. But this is just a probability. We have a total of 150 customers. So we have an E of X, so expected number of customers. So E of X is going to be the number of customers multiplied by the probability of that outcome, which is going to be the 150 customers multiplied by the probability that they wait between 8 and 10 minutes, which is the 0.2297, which gives me a value of 35.4. Again, you can't have 0.4 of a customer, so you round down to 35 customers. So yeah, that's it. Next is the manager noticed that when a particular staff member was rostered on, 30% of customers waited less than 5 minutes to receive their coffee. The mean time is still approximately 7 minutes, and they suggested that the staff member should be rewarded for good service. Use the facts above to calculate and estimate the standard deviation of time taken to receive a coffee from the staff member, and discuss if you agree with the manager's suggestion. So we have a missing parameter here, and the missing parameter is going to be the standard deviation. But we've been given a probability at a certain point, and we've been given that the mean stays the same. So graphing this situation, it's going to look like this. So the mean is still at 7. Standard deviation we don't know, but we know that 30% of customers waited less than 5 minutes, so where it's 5 minutes, and then less than that, this area is 0.3. And in order to calculate a missing parameter, we're going to compare this to the standard normal distribution. Standard normal distribution that is centered at 0, standard deviation at 1, and then we're going to bring down this value here, and we're going to calculate that Z value. That gives us an area of 0.3 on the left-hand side. So in your calculator, you use the inverse normal. You set the mean at 0, standard deviation at 1, in the area as 0.3, and the tail pointing towards the left-hand side. And so here we get a Z value of negative 0.5244. And then we're going to use the formula X minus mu over standard deviation. We know X is the 5 minutes that give us this value here. We know the mu is going to be 7. We just don't know standard deviation. So negative, this is negative 0.5244 equals to 5 minus 7 over standard deviation. So standard deviation is negative 2 divided by negative 0.5244, which gives us 3.814 minutes. So that is the estimated standard deviation, and then we need to discuss whether or not we should actually give this guy a reward. So recall that the standard deviation before was 1.5 minutes. So standard deviation initially was 1.5 minutes, and the standard deviation final of this other employee is 3.814 minutes. So remember that if there is an increase in standard deviation, there's going to be more spread, right? So this was the original case of standard deviation being equal to 1.5, but then after standard deviation increase, it probably looks more like this. It's probably a really bad one. Like this. So it's a flatter curve, and it's more spread out. So if it's more spread out, it's less consistent. So if it's less consistent, then this worker, yes, a few of them will have a higher likelihood, or more of them will have a higher likelihood of waiting less time, but then at the same time, there's also a higher likelihood that they wait a longer time as well. So because he's not a very consistent worker, it's probably not a very good thing to have customers waiting either a very, very short amount of time or a very, very long amount of time. So standard deviation increased from 1.5 to 3.814 with this specific employee. Therefore, the waiting times are less consistent. So although more customers may wait shorter times, there are also more customers waiting longer times. Therefore, I don't think they should be rewarded. Okay, next one. Some of the data that the cafe manager collected over the past week is shown in figure 1 below. So this is a box and whisker plot, and we've been asked to calculate the median, quartiles, and interquartile range for the data in figure 1 and for a normal distribution model with a mean of 7 and a standard deviation of 1.5. And then we want to enter our answers in the table below, which is down here. So just looking at the data to calculate the median we just look at where the line is. So the median is located where that line is, which is going down to 6. So the median we know is going to be 6 minutes. And the quartiles is going to be the lower quartile and the upper quartile. Lower quartile is on the left end of the box, which is going to be situated at 5. And the upper quartile in the right side of the box is going to be 8.5. And so the interquartile range is going to be the difference between the upper quartile and the lower quartile. So it's going to be 8.5 minus 5, which is going to give us 3.5. So median at 6, lower quartile at 5, upper quartile at 8.5, interquartile range at 3.5. In the normal distribution model, we have a mean of, we have a mean situated at 7, and then a standard deviation of 1.5, and we're asked to calculate the median. The median is just going to be where 50% of the data is split, so that's just going to be at 7. And then the lower quartile is situated here, where this is 25% of the data underneath it. So 0.25 to the right, to the left, sorry. And then the upper quartile, where 25% of the upper data is split. So this, again, is 0.25. And the interquartile range is going to be the difference between those two values. So the lower quartile is P of x being less than a certain value x equals 0.25. So this is the inverse normal distribution. So this is, let's say, lower and then upper. So the inverse normal, you're going to set the, for this one, you're going to set the area equal to 0.25, the direction of the tail to the left, a mean of 7 and a standard deviation of 1.5. And for this, you will get a lower quartile value of 5.99. And then the upper quartile is going to be the probability of x being greater than the upper quartile value, and this area must equal to 0.25 as well. So putting this in your calculator, this time with the tail pointing to the right, area is still 0.25, and that's going to be 8.01. And so the interquartile range is going to be the difference between those. So 8.01 minus 5.99 gives me 2.02. So here, normal distribution, the median is going to be at 7. Lower quartile is going to be at 5.99, upper quartile 8.01, interquartile range 2.02. And that's all we need to do there. At the start of this question, you are told to assume that a normal distribution model with a mean of 7 minutes and a standard deviation of 1.5 minutes can be used to model the waiting times for a takeaway coffee at this cafe. Is this assumption appropriate? So you want to use numerical evidence calculated in part I and refer to the center, spread, and shape of the data to support your answer. So in terms of the center, so we want to go through it about this in the 3 domains: center, spread, and shape. So looking at the center, you look at the mean, median, and the mode. In this case, we'll just focus on the median. So the median value for the median value from the data is 6, and the median value for the model is 7. So because they're not the same, it's not a good fit. But this can be very easily solved by setting the mean of the normal model at 6, because it's a model. You can change the variables here. So that is a very easy fix, but they didn't do that. So the median from data is 6 minutes, but 7 minutes in the model. Hence not a good fit. And then this is easily solved. This is easily solved by setting the mean, which is the mu value, at 6 minutes. And yeah, that is really it for the center. And for the center spread, you're going to use the interquartile range and the range as well. So here, interquartile range, you can compare the differences of 3.5 and 2.02. So interquartile range from data is 3.5, but normal model suggests 2.02. Because these numbers don't match, it's not a good fit. And it's much higher as well. And you can then talk about the range. So that was the interquartile range, but then we can talk about the range, which you didn't actually have stated in the question before to calculate. But the range from the data, remember this is calculated by the maximum minus the minimum. So the maximum was 15 and the minimum was 1.5. So it's 15 minus 1.5, which gives me 13.5. And this encompasses all of the data. So if that encompasses all the data, recall that in a normal distribution, right, within 3 standard deviations away, plus minus 3 standard deviations away, majority of the data here, 99.9% of the data is covered here, which is basically all of the data here. So the range that you have should be equal to 3 times the standard deviation here. So in order for this to happen, right, the standard deviation that we had initially was 1.5, which means that plus minus 3 standard deviations away must be plus minus 3 times the standard deviation of 1.5, which is plus minus 4.5. And if it's plus 4.5 and minus 4.5, in total there is a difference or a range of 9, right? So if this goes up 4.5 and then minus 4.5, right, you can see that the range here is going to be 9 because the absolute distance between them is 9. Or in other words, if you just take the max, 4.5, minus the minimum, which is negative 4.5, minus gives you plus, gives you 9. So the range from the model is 9 compared to the range of the data at 13.5. So range from the normal is 9 and the range of the data is 13.5. So this does not match. Therefore, it's an unsuitable. And in order to actually calculate what the standard deviation should be, you take the range of the data, right? So the suitable standard deviation is equal to 13.5, right? That's the range. Divide that by 2, right, to get the actual distance away from the mean, because this is 2 lots of the distance away from the mean. This gives you 6.75, right? And we know that it is 3 standard deviations away. So if we divide this by 3, we can get the actual standard deviation over here. So divide that by 3, we get 2.25. So the actual standard deviation that should have been, it should have been 2.25 minutes in order to accurately represent the range of this data. So that is commenting on the spread there. So instead of 1.5, it should have been 2.25. And then the shape of it, well, you kind of imagine Well, remember the shape of normal distributions must be unimodal and symmetrical and bell curved. Notice here that there is you would expect the peak or the mode to be at where the median is, but it doesn't really happen around there. You have a peak around here at 5 and then a peak around here at 7, and then you would kind of expect everything around there, like further away, to be nothing. But you have another unusual peak at 15 minutes where there's 3 people waiting there. So because of that, there's a peak here and a peak here. You can say that there is bimodal because there's 2 distinct peaks, right? And you would also expect it to be symmetrical, but it's not, because you can see that when you draw the line between the median, right, there's a lot more data that exists on the right-hand side compared to the left-hand side, right? Which means that because there's more data on the right, the spread is more towards the right side, so there's more skew to the right side, so it's a rightward skew. Okay, so it's a not symmetrical, and there's unusual values, or an unusual cluster of values at 15 minutes. So you say here, the shape, the data is bimodal, right skewed, and contains an unusual cluster of points at 15 minutes. So relating your data points here, bimodal. So bimodal here, that's going to be 2 peaks at 5 and 7 minutes. And then rightward skew means that it is not symmetrical. And a higher likelihood of waiting longer times, and then the unusual cluster of points at 15 minutes. So all of these do not coincide with the usual features of a normal distribution. Normal distribution assumes unimodal and symmetrical shape, which the data does not coincide with. So you can say, hence it's a bad fit. And one of the other points that you can say here is that a normal distribution model will tail off towards positive and negative infinity, which means that the distribution actually goes into the negative minutes, right? And obviously you can't have negative time because time cannot be negative. And so therefore that's another limitation of the normal distribution model. But that point is only limited to a merit grade typically, because you don't actually apply the context here, because the context and the numbers that you've been given here, you should be relating to your points. But because this point can be applied to any context really, that is applicable, where time can't be negative, weight can't be negative, that sort of thing. It's kind of like a universal thing, so that's why it's not regarded very highly. So you can also put that there. So normal distribution also considers negative wait times, which is impossible. Therefore, not a suitable model. And you can actually calculate the percentage or the proportion of how much of the data is being considered as in negative time. So again, centered at 7, standard deviation of 1.5, and then you want to calculate the proportion of the data that is less than 7. And it's going to be really small, but it's still worthwhile to consider here. So what is the probability of x being less than 0 using this data over here. So you go into stat, distribution, normal distribution, cumulative, and then variable, lower being like a crazy high negative number, upper being 0, standard deviation of 1.5 and a mean of 7, and you get 1.5306 times 10 to the negative 6. So in other words, this is 0.00000015306 proportion of the data. So that is a very, very, very small proportion of the data, which is, in the grand scheme of things, very insignificant, but still something you can talk about here. And if you want to provide the numerical values as well, or how much of the data actually takes up, then you can put that inside here, but limited to a merit grade. Okay, well, that brings us to the end of the paper. I hope that made sense, and yeah, give me a question, message me if you have any questions of this. Okay, bye.